Hello. In this video, I'm going to be solving problem 43 from section 13.2 of James Stewart's calculus. The problem asks us to find r of t if the derivative of r is given by this equation, and we're given the condition that r of 1 must be I plus j. So normally, with these derivatives of vector function problems, we're given a function like r of t, and we're supposed to find its derivative. Here we're going in reverse. We're given the derivative, and we need to find the function such that its derivative is this and satisfies this condition. How do we do this? Well, you might remember that in general, integration and differentiation are inverse operations. So for just normal functions, f prime, this is just f of x plus some constant c. And the same rule applies here, it turns out. So for a vector function, r vector t, the integral of r, the derivative of r, can be given as just the vector function plus some constant vector. One way to see this is that if we write the derivative, our vector of t, as, say, derivatives x of t, y prime of t, z of t, then remembering that we integrate component-wise, this will be x prime of t dt, integral y prime of t dt, and then integral z prime of t dt. And this in turn will be, well, it's going to be x of t plus some constant c1, y of t plus some other constant c2, and then z of t plus some other constant c3. Note that the constants here, c1, c2, and c3, do not need to be the same because we're integrating these functions separately. And if we collect everything, so we collect the parametric equations in one vector, and we collect the constants in some other vector, then we can rewrite this exactly in the form that we have above. This is r of t, and then this would be our constant vector c. This is a pretty useful fact. Here, to get some practice with integrating a vector function component-wise like this, we're going to use this approach to calculate this function here from this derivative. And so going down here, integral r prime of t dt, well, this is going to be, note here that I'm going to, you know what, to be consistent with the problem statement, let's use the I hat, j hat, and k hat notation. This is going to be, well, the x component is 2t dt I hat plus integral 3t squared dt j hat plus integral root t dt, and this will be k hats. And so just calculating these integrals, first one will be t squared plus some constant c1 I hats. Next one will be t cubed plus some other constant c2 j hat. And then finally this one, just doing a quick mental power rule, this will be 2/3 t to the 3/2. 3/2 plus some other constant c3 k hat. Which, if we want to write it in a slightly more convenient way, namely in this form right here, we can just collect all of the functions into one vector and all of the constants into another vector. So this will be t squared, actually, there we go, t squared I hat plus t cubed j hat plus 2/3 t to the 3/2 k hats. So then this would be our or it's not r of t quite, but this is like the part of the vector that depends on t. And then our constant vector, and you know what, just to avoid confusion with that fact, I'm going to highlight the constant vector only. Let me put parentheses around this, and then our constant vector is just going to be c1 I hat plus c2 j hat plus c3 k hat. And then this is our constant vector. We're going to call it c vector. Okay. And again, over here, this is going to be just r of t. And here we have our constant. And all that remains is to find out what the values of C1, C2, and C3 have to be. And this is exactly where we're going to make use of this other condition that they gave us, that r at 1 should be just I plus j. And so just plugging things in, I hat plus j hat must be our vector evaluated at 1. But on the other hand, using the expression we just found, this is going to be, well, here in the parentheses, it's going to be I hat plus j hat plus 2/3 k hat, just plugging in 1 to for each of the parameters t. And then on the right, we're going to get c1 I hat plus c2 j hat plus c3 k hat. And if we collect like terms, all the I hats, j hat, and k hat terms, this is going to be 1 plus c1 I hats plus 1 plus c2 j hat plus 2/3 plus c3 k hats. And so equating coefficients on these two sides, remembering that because there's no k hat on the left, the component for k hat here is just 0. We get the equations 1 equals 1 plus c1 for the I hat components. We get 1 is equal to 1 plus c2 for the j hat components. And then finally, we get 0 equals 2/3 plus c3 for the k hat component. And solving for the constants, we get, well, c1 is 0, c2 is 0, and c3 is negative 2/3. And so, just jumping over to another page, our final answer would be that our function is t squared I hat plus t cubed j hat plus, then the k components is 2/3 plus t to the 3/2 k hats, and then plus the values for c1, c2, and c3 that we got. So this is 0 I hat plus 0 j hat minus 2/3 k hats. And again, just collecting all the I hats, j hats, and k hats. This is t squared I hat plus t cubed j hat plus 2/3 t to the 3/2 minus 2/3 k hat. Okay, that completes this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.